Today, we are diving into our analysis of a laptop pricing dataset sourced from Kaggle. Our primary target is to predict laptop prices, a continuous variable based on features like brand, processor, and memory configuration. To achieve this, our project follows a three-step strategic methodology. First, we focus on data engineering to clean and transform the raw data. Next, we conduct EDH and cover statistical distributions. Finally, we implement linear regression and decision tree models to compare how data cleaning impacts predictive performance. Our goal is to ensure a robust and accurate pricing model. Before we analyze the data, let's look at our feature architecture. We have categorized our 11 variables into three main groups. First, brand and classification includes the manufacturer and specific type of laptop. Next, we have core hardware, which details the CPU, RAM, storage capacity, and GPU. Finally, screen and physical specs cover display resolution, screen size, and portability factors like weight and the operating system. Understanding these features is crucial as they directly influence the local currency cost, which is the value price column. Our first diagnostic phase revealed several structural integrity issues. We found a uniform sparsity across the dataset with approximately 30 missing values per field. We also identified structural noise, such as a redundant index column. And furthermore, data types are contaminated. For instance, numerical fields like RAM and weight contain unit strings like GB or KG, preventing direct calculation. Lastly, composite fields like CPU and memory store multiple attributes in a single string, requiring a split for effective feature engineering. In the second diagnostic phase, we shifted our focus to logic and accuracy. We detected significant outliers, such as a laptop weight of 0.0002 kilograms, which is physically impossible, and screen sizes exceeding 35 inches, likely due to unit errors between cm and inches. Classification errors were also present, with notebook misspelled as netbook and inconsistent OS labels like macOS versus macOS X. Additionally, we identified 29 completely duplicated records that would skew our statistical.
In the raw dataset, this data was stored as string containing units like GB and KG. This presents a problem because machine learning models cannot process text mathematically. To solve this, we applied a three-step process. First, we used the function string split method to separate the numerical values from the units. Second, we extract just the pure portion. Third, the most importantly, we used the function astype to force convert this string into the floats. During this process, we also focus on the data integrity. We detect a outlier in the weight column. A laptop listed as 0.0002 kg, which is just 0.2 grams. Physically, this is possible. We identify this as a data entry error and manually correct it into 2.0 kg to ensure our dataset reflects reality. Next, we moved to a more complex challenge, unstructured text mining for the screen resolution column. The raw data here contain a mixture of marketing terms blended with actual resolution numbers. To address this, we used regular expressions. This allows us to extract just the resolution, like 1920 by 1018 from the noise text. The step involved designing a classification function. Our function determines the display type based on the resolution's width and height using the following criteria. For example, 4K is greater than 13,814 by 2116. We then applied this conversion in batch and verified the results as shown in the figure.
Moving on, the CPU model, the raw data presented a challenge because information like brand model and speed were all mixed into a single stream. We first used regular expressions to extract the brand and speed. However, the real issue was the model name. It was too specific, like i7-770HQ versus i7-7500U, which would cause model overfitting. To solve this, we applied a dimensionality reduction strategy. We grouped specific models into their core series, such as Core i7. As you can see in the box plot, this cleaner data reveals that Intel has a long-tail distribution, confirming its dominance in the premium market sector. Next one is the memory model, which it contains the dirtiest data in the dataset. We encountered hybrid configurations like 1 TB HDD plus 128 GB SSD. Simply keeping it the first number would result in losing critical value information. We designed a specific parsing algorithm for this. Firstly, it splits the stream based on the plus sign. Second, it detects TB and converts it to 1024 GB. Finally, it maps the capacities to 4 separate columns: SSD, HDD, flash, and hybrid. For example, a hybrid entry is automatically split. 128 goes into the SSD column, and 1024 goes into the HDD column. Why did we spend so much effort cleaning the memory column? The result justified the work. After converting the text to numbers, we analyzed the correlation with price. We found that SSD storage has a correlation of 0.67, making it the second most important feature in the entire dataset. Interestingly, HDD storage shows a negative correlation. The allies with the marked trends where large mechanical drives are now mostly found in cheaper budget laptops. This provided our complex feature engineering successfully turns unstructured noise into high-value signals for our model.
Hi, my name is Chen Liang. I will talk about how we improve the data. First, about screen resolution. The original data was just text like 1920 by 1080. Computers cannot read this. So we created a new feature called PPI. It combines screen size and resolution into one number. This tells the model how sharp the screen is. Second, about price. We found that most laptops are cheap, but a few are very expensive. This is bad for the model, so we used log transformation. This made the price data more balanced and really improved our accuracy. Next, let's look at text columns like company and CPU. There are too many brands. If we use standard encoding, the data becomes too messy. So we use target encoding. Please look at the chart. It shows a price ladder. Better CPUs have higher average prices. We used these average prices to turn text into numbers. This helps the model understand the value of each brand. However, we found a bias. Our data is mostly Intel and Windows. So, For small brands like Huawei, our prediction might be less accurate. We are aware of this limitation. Finally, let's look at the results. We compared linear regression and random forest. Random forest is the winner, with 89% accuracy. So why is it so good? Please look at the impact of transformation chart. You can see the R2 score went up after we fixed the price distribution. This proves our math adjustments worked. Now, look at the bar chart. The most important features are RAM and PPI. They matter more than the brand name. This proves our cleaning work was critical. If we didn't clean the RAM or calculate PPI, the model would miss these two key factors, and the accuracy would be much lower. To conclude, our team successfully went from dirty raw data to a smart, high-accuracy model. That is the end of our presentation. Thank you for listening.